is Dr. Andrew J. Younge, who is a computer scientist in the Scalable System Software Department at Sandia National Laboratories, New Mexico.
There we go. Helps if I take myself off mute. Well, thank you, Samir. Guess I'll get going here. Move some things out of the way. So I'm going to talk about sort of our effort towards containerized HPC and the related applications heading towards Exascale here. This should be a pretty basic talk. We've talked about containers a lot in this forum already. So I'm going to try and bring a little bit of background to it, and then sort of how this has turned into what we're calling supercontainers. And then I'm going to focus primarily on two aspects: building and running these containers, specifically for HPC environments. And then I'm going to try to leave you with some, future work, thoughts, and that sort of thing. So why don't I get started? So first, let's make sure we understand what we're all talking about here. I think everybody's heard about containers. If not, I don't know where you've been, but it's essentially supposed to be the single unit of, a unit that packages up all your code and software dependencies that's necessary to execute some task. In reality, this is true of everything that is basically user level. So your kernel isn't included in this. But otherwise you could think of it as your entire user space software ecosystem. Another word or term for this is OS level virtualization. However, it's important not to think too closely in relation to virtual machines. This is more sort of CH root on steroids, or a BSDJL, if you will. Depending on your host operating system, and you can pick whatever operating system you choose, so long as it's Linux. And it uses and leverages various Linux namespaces that we'll get into in a little more detail. Most people that have heard of a containers have generally found Docker and use Docker in some context, I would say, for their usage. And this is sort of the common tool that we see continually in the cloud. So there's what I would call a bit of a cloudy relationship here with HPC. Obviously, public cloud computing usage across the DOE is often prohibitive, not only from a cost perspective. I mean, we build very big leadership class machines for a very good reason. And there's also, a large security aspect. What happens to my data or my simulations that maybe, let's just say, proprietary when I push them to a public cloud. The problem with this is that, HPC is traditionally not nearly as flexible as, quote unquote, the cloud, if you will. We rely on shared resource models. We have a pretty, I would say, a pretty good history of static software environments. And, many of the new tools require modification that, any common COTS tool that maybe you'll find in the cloud. And recently within this quote unquote cloud model or the hyperscaler industry, containers have become sort of a primary deployment model for software. So that sort of leads us into some interesting questions here. What about containers and what about their usage in HPC? Can we really support containers in HPC the same way in which clouds do? I'm basically going to argue both yes and no here. Does this model fit for both our traditional HPC applications and some of the more emerging workloads that we're seeing across the DOE, including ML, AI, data analytics workloads, et cetera? And can we adapt, our current programming environments into container images? And generally the answer here is yes. So with this, we sort of create a bit of a vision here. The idea here is we could develop our software specific for HPC and our large-scale supercomputers on, say, laptops and workstations, which isn't something that's easily done today without containers, for instance. We can create these working container builds that I could then hypothetically move and transfer to a supercomputer and run. And maybe this helps minimize my development time and better utilize my resources. Really taking upon this notion that we can scale and move our containers up to leadership class supercomputing resources. The real power with containers really lies in the ability to have direct specification of how to build your software environment and the application in which you're trying to deploy. You know, this could just be something where you could hand to a user, an analyst, and say, here you go run this on your computer. You could have different manifests, different target platforms and deployments. We'll talk a little bit more about this. And we have the potential, this is both good and bad, to not be bound by, say, vendor release cycles or other system administration requirements or responsibilities and whatnot. So eventually what we'd really like to do is get towards, really enabling this full scale sort of custom software ecosystem. And a lot of this is represented in the ideal that is E4S. And we need to do this in such a way that performance really matters. It's called HPC for a reason. We've done a lot of work already sort of shaking out container runtimes, using mini apps and full scale applications. I'll get into this a little more. And then we really need to expand this to Exascale, while also simultaneously making sure we're still doing a good job at supporting some of these more emerging workflows that we're seeing across the DOE. So with that, sort of created this super container effort. And this is sort of while I'm the one talking to you, this is a much larger effort than just what I've put forth across several organizations and individuals in the DOE. And really what we're trying to do is ensure that these container runtimes will be scalable, interoperable, and potentially, hopefully, well integrated across the DOE in time for the first Exascale machines. Maybe we could try to enable this sort of laptop to Exascale vision that I hinted at previously. And we also have this directed effort to really help some of our software development and application teams, as well as facilities, in leveraging containers most efficiently in whatever that may entail. So there's several components to this project. I'm going to talk mostly about some of our R&D activities, sort of where we're at. We also spend a lot of time, as mentioned, trying to collaborate with other projects, as well as putting together training, education, and support services. As a quick plug, we will have an SC20 online tutorial about just this. And what we really are trying to do is conduct these activities in the context of interoperability, and have some hope of creating portable solutions that are still optimized to run on various architectures. But we're not really looking to sort of select a winning container runtime, if you will. And we'd like to make sure this stuff works across multiple facilities at multiple scales. This is not a one and done, so to speak. So now I'm going to get into sort of some of our recent work with building container images. Now, I'm really cheating here from Samir and borrowing a slide from him. I'm sure most people are aware of E4S and the current state of it, but there's a quick slide here to really just kind of recap this. The important thing I would say for us, or my talk, is that E4S is being delivered via containers through a lot of Samir's work, and they're available already on Docker Hub for multiple different architectures across multiple different operating system distros. And we're starting work, which, both I would say Ryan and Todd did a great job of describing in sort of this containerized CI effort that I think is coming. And we're going to see a lot more support for additional hardware like GPU. So wanted to give a quick shout out and pointer to that. So now that kind of sort of explains how all this ties together. I'm going to focus more on sort of the abstractions that we need. And it's important to point this out. Todd and I have both worked on this perspective. And it's important to define, this performance portability continuum. And it's about striking the right balance, not selecting one or the other, I'd argue. Containers have this new ability to enable users to have some sort of movement of their software ecosystem. And that's a really powerful notion, but it is potentially a dangerous one if not used properly. And so we really want to start focusing, making sure developers focus on what they're trying to do in terms of a deployment strategy. Are you going to focus on a portable solution? You're really going to care about reproducibility, and you're okay making some performance sacrifices. Building for a lower target, target ISA, and maybe not worrying so much about leveraging the latest GPU drivers, for instance. Or are you really at the bleeding edge and you need every bit of exascale performance, and you require multiple targeted builds for custom or boutique hardware, which we often see in HPC? And are you doing absolutely everything possible? But you're only focused on one system in particular. I'm not saying there's any right or wrong answer. I guess I'm trying to put this continuum in front of people to make sure they're understanding that this is something that there is no right answer, and you know, probably it's, you know, there's going to be some movement somewhere in between here. So one way in which obviously has been mentioned previously to sort of alleviate some of this is for us to actually pay attention to what our ecosystem looks like. And one way in which we can do this is working with, you know, dedicated user level package management. And this is with SPAC in particular in this case. I've cribbed this sheet, this slide directly from Todd, and it's an old one, but it shows really just how quickly we can put together and use SPAC, which is, you know, a really powerful package management tool for HPC, directly in a container. And these end up being quickly complementary tasks. Again, another quick perspective that I've tried to put together quickly in a visualization, and really trying to be able to deliver on this fact that, you know, if I am a developer, I want to generate my own container build, maybe not from pull requests, but an official release, and have a container built such that I can quickly test and deploy my code on a real target HPC machine. We're still trying to define what this build farm looks like and how we really manage this effectively, but this is sort of really what we're trying to do. And I'm using Singularity as an example in this case, but it applies to many different runtimes potentially. So one of the things we've really tried to focus in the context of interoperability is really sticking with OCI, or Open Container Initiative based images. This is a really important feature. It's very similar to really the Docker format. It started originally from the Docker v2.2. And it's, you know, pretty much a community-driven effort that we're really trying to engage with an HPC-specific focus at this point. And what's important here is I can build these container images using several modern container runtimes, obviously Docker, but also Podman, Builda, and Cryo. There's another one every day, right? And I can also run these on not HBD, but HPC container runtime. So Singularity Shifter, Charlie Cloud, Saurus, Inception, you know, just another container runtime. You know, they generally will support OCI-based images. And I can leverage a multitude of registry services that now exist within GitLab, OpenShift, there's Harbor, there's many of these different container registry services that I can leverage, and they all work with these OCI images. So while we may have a diversity in our container runtimes, which I'll show and explain in a little more detail, we can focus on one sort of method for creating images. So one example of what we're trying to do is really sort of manage system libraries that get brought in at runtime for performance. And one of the efforts we've been trying to do in prototype to some extent, for instance, with Shifter here, is trying to use image labels and let that create a hook, if you will, into the container runtime that will make the right runtime decisions on what libraries you need and take care of some of the initial wire up to make some of the pain points that we see with custom libraries. I'd say this is a bit of a stopgap, but it's an interesting take at the moment, and I think we can continue to improve upon this. This is another feature that I would say is really coming to fruition recently, and we've got a proof of concept here that I want to walk through. So, for instance, I'm going to talk about this Astra machine here at Sandia really quickly, just as an example. For those who don't know, it's a petascale ARM64 machine, and my Mac doesn't yet look like a ARM machine. So I can't quickly build container images, say on my laptop or my average workstation sitting under my desk, and be able to run them on my ARM-based supercomputer. You could assume you could have this same problem with any other non-standard or boutique architecture if you're not careful. So what we're trying to do is enable sort of user space container build tools. And we've been able to work with Red Hat on Podman and Builda to provide this functionality and test this out on Astra. This uses user namespaces. We do some tricks to sort of manage, you know, sub-UID and GID mappers. And really what we can do is build directly as a user, as my user, AJ Young, my container, which has the base software environment, say for Astra, and be able to then push this to a standard container registry service in GitLab, deploy it with Singularity, and run it on a couple thousand nodes. This is a bit of a powerful notion and something that is only proof of concept, but I think we're going to see coming to fruition in the next year. So that gives you sort of a quick perspective about how we're focused on building containers in this context. Now, what about, you know, sort of some examples of running containers at scale? This is petascale, exascale. Well, we'll see, right? So as I mentioned, you know, there's many different HPC container runtimes. And this is really due to the fact that Docker is not a good fit for HPC as is. Docker is essentially equivalent to root, which is why you know, these tools aren't useful for running or building unless I already have my own dedicated supercomputer all to myself. As these resources are almost always often shared, we need to make sure that you know, these deployments and running of container images stay within user space. So the good news is we've got multiple container runtimes, and they're all really usable in the context of HPC today. They offer different, you know, design and OS mechanisms to employ these technologies, but generally they're all doing something very similar. Some of them also, you know, offer additional image support, say with Singularity, or some signing and validation functions, et cetera, et cetera. But the good news is you could use any one of these today for your supercomputer if you wanted to. And we see exactly that across the DOE. This is sort of a quick snapshot that is continually changing. I don't want to, like, you know, pin anybody down here at any particular site, but you could see a wide array of different container runtimes being used across the DOE. And this is okay, right? We want our facilities at each site to have the flexibility to choose what they need for their current deployment and for their users. It's our job to interact and help facilities really be able to use these tools effectively at scale too. And be able to develop consistent images that could run across multiple runtimes here. So part of the reason I say, you know, all these are pretty usable is because we've seen an interesting paper recently that shows, you know, the performance is all pretty similar and they all have minimal or no performance impact, you know, when you use them properly. There's some slight variance. I would say this is probably mostly due to, you know, it's within 1% often, and it's largely due to variance that you're going to see naturally across any, you know, any shared resource environment to begin with. So this is generally good news. It's not always the case, but we also need to, we've got a good, you know, sort of standing point now for evaluating this. We need to make sure we can repeat this and demonstrate it effectively at Exascale as well. So that's not to say our work is not done. Another example is one we've worked with Sandia's Spark application, an ATDM-based application. And we've deployed this again on Astra with Singularity, and we've seen near native performance at full system scale of thousands of nodes. Here in this example, you could see I made the container slightly faster because if I didn't, the two lines would look absolutely identical and it'd be a very boring graph. It already is pretty boring. However, for the containerized approach, I was quickly able to add some new optimizations that the vendor had provided us and recompile my code. And turns out I could quickly evaluate that, yes, at scale, my code now is, you know, 4% faster. And we could measure that variance across several runs. So that allowed sort of this quick prototyping practice to be put into place. Okay, I hope Dan's still on the call here. I quickly whipped up this slide right before my talk because I wanna make some points here. I of course love Torsten's Twitter post about the dark side of containers. You know, some of this is true, but I feel like this is analogous to, you know, I'm going to use a Christmas reference, even though my Jewish grandmother may be a little upset, but it's like taking a whole bunch of really delicate Christmas ornaments, putting them in a box, right? Because a container is really just a box. And I finally have this capability for the first time. And then I hand it to my little sister who promptly throws them down the stairs and breaks them all. Why am I blaming the box for that problem, right? I should be blaming my little sister. for not doing a better job at handling this box, and myself for not doing a better job of organizing how I pack these things efficiently in the container. So I think containers have enabled a new problem, but this isn't the fault of a container runtime. It's a fault of how you're constructing your container images. That being said, those steps are sharp and can cause issues. And that is something that I think we need to continue to work on. So with that, maybe you could carry this analogy over to the stairs being, various vendors. Some who make container enablement easier or harder depending on sort of what we've seen from a historical standpoint. So a lot of what we're trying to do is work with these vendors and engage with them to actually try to enable a container native approach to software deployment, because we really need these solutions to not only be able to run our containers on these first Exascale machines, we need them to actually be performant as well. And so we really want to be able to have the vendors provide us with optimized base container images. I should be able to bring the entire programming environment that my vendor provides, for instance, Cray, and be able to build a container from scratch using all those tools. And how do I make sure I have the latest GPU tool chain enabled for getting true performance? I think once we realize this goal, we can really start to stretch our wings with containers and take advantage of some really interesting capabilities that we're only starting to get to. Release testing. I can test my entire new E4S software stack before actually rolling it out and deploying it on hardware. This has been a really important thing. I can also do rollback testing. That new version of my software, which has this new version of Torrelinos and E4S, turns out there's a bug and I didn't know about it until 2 months later. And so now I can compare this to an older version and do some rollback debugging along the way. We have actually seen this as part of some of our ATDM activities, and this being a really, really important feature that we didn't really expect to be able to provide, at least at first glance. And cross-system software synchronization is a really important thing, especially for labs that have test systems that are smaller versions of larger machines where we may develop our codes initially, say at Sandia, but then be able to deploy them on larger Exascale machines that aren't at Sandia, say at Oak Ridge, for instance. Being able to keep these software ecosystems synchronized or not have to worry about the synchronization at a user level is a really powerful notion that I really think we're going to be able to enable here moving forward. And yeah, we can fix some of these problems along the way. Maybe we could stop doing all this, hot swapping of our libraries at runtime if we don't need to. Can we actually get rid of or start avoiding, once we stop doing that, some of the glibc compatibility issues? Maybe not indefinitely. I'm being a little tongue-in-cheek here, but I think we could do a better job at some of this today than we do today. And this really is a lot of vendor engagement and working with our partners in industry. So containers and reproducibility. Everybody asked me about this, and I think there's not a simple answer here, because containers alone are not the answer. I think they could be part of a larger solution if we want to. And this is actually a really important problem. We rely on a lot of modeling and simulations for stockpile stewardship, for instance, that we need to do a lot of runs, and we may not understand the true importance of any particular run until years later. And we need to be able to have some notion of reproducibility to go back and look at some of those simulations as these studies take a very long time. Having some new method and capabilities to at least provide some hope of being able to do this, I think is a really important notion for really providing good science. So let me try to quickly wrap up here, as I'm probably running out of time. I think containers will be a viable software deployment model for the first Exascale platforms, and we're working very hard to enable that with our full partners across the DOE and our industry partners as well. I think there's been a number of demonstrated value for some of the container models, deploying initially on test beds and scaling up to our current sort of pre-Exascale or petascale machines. And we're starting to see that some of those modern DevOps approaches that some of the others earlier today have talked about and touched on, potentially with some container image generation enablement, could be a really powerful notion. So all this is sort of put together in this, notion of supercontainers where we're really focusing on the efficient build and execution of these images. And I really think E4S is going to be our #1 tool to really prove out this framework at Exascale. And it'll be our first full, really capable software stack that embodies a lot of what ECP has worked so hard for. To really be able to deploy this with a container is going to be a powerful notion. Maybe eventually, I'll leave this sort of food for thought, maybe we could get to a new default way of doing software deployment. Maybe this could be partially with containers or not. I'll leave that up for debate. And I'll conclude really quickly just saying I happen to be talking to you today, but I've leveraged a lot of help from a lot of different people, not only at Sandia, but across the DOE. So thank you to all these people and many more. With that, I think I'll wrap up. Thanks. Hopefully I wasn't on mute the entire time.
Great talk, Andrew. There are some comments in the chat from Dan.
Cool. Let me pull them up here. It's a good sign. Yeah, we're making Torsten famous. Maybe. Yep. Let's see. We don't think it's containers' fault either. They've just provided a convenient excuse for not dealing with the real problems. That's exactly right. Good. I think we're on the same page then. It's really cool that we have this ability to build an ecosystem that I care about and be able to move it all around. But we shouldn't be too surprised when that causes cascading issues. That's not a reason to not work and fix those issues. I think it's an important thing for the community to really work with. And a lot of this, again, as I hinted at, requires some vendor engagement along the way. Let's see. I made the important distinction, and I think is lost on many, between the container as a binary image and the recipe for containers, which allows us to build them correctly on, exotic architectures. Yes, I think that, at the end of the day, a container image sitting in a registry may be far less useful than the actual Docker file or the OCI spec and the build manifests that produce that image. I think that's sort of where that special aspect is going to be when it comes to trying to reproduce a work years later, for instance. It's less about bitwise reproducibility. It's about understanding what was in my container and how did I install it? And what does my software ecosystem look like? So, cool.
Well, thank you very much.
Thanks, Samir.